This talk presents GeoNerf, a generalizable neural radiance fields method for rendering and synthesizing novel views in a static scene. Original radiance field method, as known as NERF, is capable of rendering high-quality novel views with consistent geometry and appearances. However, this model requires per scene optimization, and it should be trained on each individual scene separately. Later, generalizable methods such as MVS-NeRF introduced a single model that can generalize to novel scenes too. However, the rendering quality gap between the existing methods and the original NeRF model is considerable. Our proposed model, GeoNeRF, reduces this quality gap between existing methods and the per scene optimized NeRF model and renders detailed scenes with consistent geometry. To render a novel view, our method assumes that we have access to V nearby source views. To understand the geometry, we construct cascaded cost volumes for each of these views. In this regard, we first extract multi-level 2D semantic features from these images with a feature pyramid network. Then, by constructing hypothetical depth planes and using homography warping techniques, we create multi-level cost volumes from these feature pyramids. These cost volumes are regularized with the 3D CNN network and output estimated depth map and 3D features at each level. We call this architecture cascaded because depth planes of each level depend on the previous level estimated depth map. The resolution progressively increases in these volumes, but in the depth dimension, these volumes progressively become thinner. For rendering a novel ray, we sample endpoints along the ray, and for each point, we interpolate 2D features and multi-level 3D features. We then create a view-independent token by calculating the mean and variance of the 2D features across all the views. We also create view-dependent tokens by simply concatenating the 2D features and the 3D features from each view. Here is the summary of our geometry reasoner. We use FBN to extract 2D features. We then use warping techniques to construct cascaded cost volumes. And then for rendering a novel ray, we sample endpoints along the ray. And for each point, we extract one view-independent token and view-dependent tokens. The data in these tokens are aggregated with 4 multi-head self-attention layers. The resulting tokens are then divided into 2 separate paths. First, the view-independent tokens are regularized along the ray with an autoencoder network and predict the volume densities of all the points. On the second path, the view-dependent tokens are supplemented with positional encodings and predict the weights with respect to all the source views. The color samples from the source views are blended together in a weighted sum fashion and predict the color of all the points. Finally, using the classical volume rendering technique from the NeRF, we render the final color value of the ray. The ray colors and depths are rendered with the classical volume rendering technique. These colors and depths are supervised with the ground truth values from the training samples. In addition, we also supervise the depth maps estimated with the cascaded cost volumes in the geometry reasoner. GeoNeRF outperforms existing generalizable NeRF models with a high margin. Also, after fine-tuning for only 10,000 iterations, its results are competitive with the original NeRF model. Qualitatively, GeoNeRF produces more realistic images with fewer artifacts. Here you see some example scenes rendered with our model. On the left, you see the videos rendered with our generalizable model, and on the right, you see the results of our model after fine-tuning on each scene. Thank you for visiting our website for additional qualitative analysis and also the implementation source code.